Assalamualaikum. My name is Anis Syuhada from K12 and my group mates are Yolipkin, Muhammad Firdaus and Nur Hajaratul Akmal. Today we would like to present on our final year design project. The theme for this project is production of raw material from renewable resources for non-alcoholic base hand sanitizer. So the title that we choose is the production of sorbitol from dried empty fruit bunch EFB. Our supervisors are Prof. IR Dr. Muhammad Sobri Takrif, IR Dr. Teo Yit Han, Sir Muhammad Fitri bin Las, and Sir Ridwan Afendi bin Abu Bakar.
Based on the theme given, we decided to produce sorbitol as our main product. Sorbitol is a sugar alcohol and has the role as sweetening agent, a laxative and also humectant. And as for the hand sanitizer, sorbitol will act as humectant. The table on the left side shows the chemical and physical properties of sorbitol. As for our raw material, we decided to use dry empty fruit bunch (EFB) from the waste of the palm oil. We already did the comparison between three types of raw material, which is EFB, pineapple waste, and also coconut coir fiber. We did the comparison based on the cost and the glucose content, as our main product will be using glucose undergoes hydrogenation process to produce sorbitol. And we found out that EFP contains higher glucose with low cost. Thus, EFP is selected for our raw material. Next, for the supply and demand, the graph shows the supply and demand of sorbitol. And referring to the supply and demand of sorbitol, we decided to build our plant with capacity of 750 kg per hour or 6,030 tons per year, which covers 0.75% from the shortage of sorbitol.
Hi, I'm Yo and I will be presenting the future economic potential for the FEP4. It is estimated that at around 90% of conversion, our FEP is around 118 million ringgit and our product will be sold at 16 ringgit per kg. For the profitability analysis, the production rate of sorbitol at full capacity is around 6 million kg per year. The total capital investment is around 130 million ringgit and the cost of manufacturing is around 32 million ringgit. Moving on to the break-even analysis, here it shows that the break-even analysis showed a gradual increase in income in the first few years because the production rate is also increasing in the first few years, as we estimated the production rate of our company will be lower in the first few years. And then for the ROI is around 0.2 per year, and the payback period is around 1.62 years. And then the net return is around 15.2 million ringgit per year, and the NPV is around 143 million ringgit per year.
This figure shows our PFD after heat integration. Raw EFB will enter the plant and undergoes pre-treatment process. Next, the hydrolysis process will be done in CSCR with the ratio of solid to liquid is 1 to 10. The outlet of the CSTR will then undergo two separation units, which is centrifuged to completely remove solid components before entering fractional distillation column. The bottom product of fractional distillation column, which is glucose, will enter the fixed bed reactor and undergoes hydrogenation process that will convert into sorbitol. The outlet of FBR will enter flash drum to separate hydrogen gas and finally enter an evaporator to separate excess water to obtain final product, which is 70% sorbitol. For wastewater treatment plant, since our organic matter is a non-biodegradable, it will undergo a chemical treatment first, then biological treatment. The effluent will enter bubble column reactor and then separated to separate the off gas. After that, it will enter equalization tank and sent to coagulation and flocculation tank, where aluminium sulfate is added as flocculant. Then it will enter the first clarifier and aeration tank to remove excess COD and BOD. Finally, it will enter second clarifier to remove excess suspended solid.
Next, for the plant location, we already did finalize three proposed plant location, which is kawasan perindustrian Kelapa Sawit Kuala Johor, kawasan perindustrian Taj Valley Negeri Sembilan, and kawasan perindustrian Bercham Ipoh Perak. And based on previous presentation, we still choose the kawasan perindustrian Kelapa Sawit Kuala Johor as our primary site location for our plant setup. And the next is our plant layout. With the land size is 60 acres and the wind direction is to northeast. Based on the plan layout, we already consider a few safety aspects. The first one is the location of the main production area, which is located far from the administrative area. This is to minimize the risk. Next is the location of the main production also near to the storage area, which could ease the transfer of chemical and material. Hence, this can reduce the cost of the piping. Next, the wastewater treatment plant also located near to the main production area to ease the transfer of the waste. As the main production area is in the high-risk area, we already placed the emergency response team to the area. And next, there are also areas for the future expansion located inside the main production area.
Okay. For the process safety, there are several acts and regulations. The first one is the Environmental Quality Act, which is for the industrial effluent, clean air, and industrial waste. For the Safety Head Officer Regulation 1997, this is one act because of the chemical industry with more than 100 employees need to the safety head officer. The next one is the use standard or exposure chemical hazardous to health regulation. This is because the hazardous chemical exposure to high concentrated sulfuric acid and the high pressure of hydrogen gas and the carbon dioxide. Okay, the next one is the control industrial major accident hazard regulation 1996. This is because the high pressure and high flow rate of carbon dioxide they more cause explosion due to overpressure of reactor. This is because our quantity hazardous substance is more than the threshold which is 21 tons more than 10 tons. For the next one is the Factory and Machinery Safe Health and Welfare Regulation 1970. There are three regulations that comply to our plan, which is Regulation 16, 17 and 32.
Next is the hierarchy analysis. After doing the hierarchy analysis, we find out that the operating the R101 and operating the R102 obtain the highest score of risk. This can cause the internal corrosion and erosion of piping system, rupture of wall of reactor, and also overpressure of reactor. Thus, recommended control measure is introduced, such as leakage indicator, level controller, emergency alarm, schedule inspection and maintenance regularly.
R102 is one of the critical units since it undergoes a hydrogenation process that operates under high temperature and pressure. The hazard for R102 consists of 4 nodes, which are for stream 25 that controls the inlet flow, stream 29 that controls the inlet pressure, stream 30 that controls the outlet flow, and the inside of the reactor that controls the flow of the cooling water. Next is the piping and instrumentation diagram of the hazard. The type of controller that were being used is temperature, flow rate, pressure, level, and composition controller. After hazard has been done, some action has been taken to ensure the safety of the plant, which is by installing a low and high alarm and a bypass valve.
Next, for the detailed mechanical design of R101, I was assigned to design the R101, which is the CSTR reactor. R101 is CSTR reactor that will undergo acid hydrolysis process, which the main purpose is to convert cellulose to glucose with sulfuric acid as catalyst. There are 3 inlets for R101, which is the stream number 8, 9 and 10. The stream number 8 consists of components extracted from the pre-treatment process, and stream number 9 consists of the sulfuric acid, meanwhile the stream number 10 consists of water. There will be one outlet for this reactor, which is the stream number 11 that gives the outlet flow rate as 58080 kg per hour. The operating temperature of the process is 65 degrees Celsius, with the pressure is maintained for 5 bars. Okay, next for the design. The material construction chosen is stainless steel type 304. Stainless steel type 304 is chosen since it withstands high temperature and corrosion resistant. It also has smooth surface that will make it easy for the cleaning process and to avoid contamination during the process. The type of reactor used is continuous stir tank reactor (CSTR). CSTR is chosen since we want our process is incontinuous. This CSTR will be using multiple flat blade turbine as the impeller for a better mixing. The reactor is designed with 7.22 meter of the height and 2.04 meter for its diameter, and the height for the jacket is 3.55 meter. And after few consideration, the shape of the reactor is designed as cylindrical for its shell and ellipsoidal for the bottom head and top head. The wall thickness is 5 mm with the correction allowance is taken as 2 mm. After performing the stress analysis, the total maximum stress is lower than design stress. This proves that the design is safe. Next, we did the elastic analysis, and after the calculation, the maximum value of compressive stress is not exceed the critical stress, and this gives the result of the analysis that this design is safe. The type of pressure support used is conical skirt support with the thickness is 15 mm and the height is 2000 mm. The type of flange used is the welding net flange. Okay, so this is the mechanical drawing for CSTR that show the front view of CSTR reactor, top view of the CSTR, and the cross section of the inlet and outlet. There will also the conical skirt support and the flange design.
The table above shows the design specification for detailed and mechanical design for fixed bed reactor R102. The material of construction is stainless steel SA240 type 410 with operating temperature and pressure of 200 degrees Celsius and 40 bar respectively. The type of head for top and bottom is ellipsoidal and cylindrical body. The height of reactor is 2.01 meter with the diameter of 0.42 meter and wall thickness of 30 mm. The type of vessel support is straight skirt support with thickness of 15 mm. The type of flange joint is welding neck flange. This figure shows the mechanical drawing of FBR that shows the side view cross-section of reactor, cross-sectional view of reactor, top view of reactor, support of reactor, and the welding neck flange.
Moving on to the mechanical design and detailed design of the evaporator 101. Here we are having an evaporator to separate the sorbitol and the water to increase the purity of the sorbitol. It is operated at 120 degrees and 2 bar. So here we can see that what is going in and going out. And here we have chosen the type of parameters. So we have chosen a ellipsoidal 2:1 ratio head because it is easily manufactured and more economical. And then we are using a carbon steel type 316SS. This is because it is considered as a weldable steel and it has a lower cost. And for the type of flange, we are using a welding neck flange because it is resistant to heat and it's durable and better at preventing leakage. And we are also using a stretch skirt support. This is the mechanical drawing of the evaporator. It consists of a calandria unit and a separator unit. For the calandria unit, the height is around 5 meters, the outer diameter is around 843 millimeters, and the thickness is around 5.2 mm. For the separator unit, the height is around 2.6 meters, and the outer diameter is around 868 millimeters, and the thickness is around 5.2 millimeters. So this is we are using a stretch skirt support, and then this is the single plate with a gusset used for the skirt support, and then we are using a triangular pitch. Okay. And this is the dimensions for the flanges.
Okay, for the design of the cooler C103, there are one component in this cooler which is glucose. The temperature inlet is 540 degrees Celsius and the outlet is 200 degrees Celsius. The pressure, operating pressure is 3 bar. Okay, this one is the design that I calculate for the tube side and the shell side. So the pressure drop for the tube side is 2.085 kilopascal, and the shear side the pressure drop is 7.98 kilopascal, and the number of tube we use is 82 tubes. Okay, this one is the mechanical design. The operating temperature is 540 degrees Celsius, and material used is carbon steel A516 grade 17. Okay, the minimum thickness is of 6.4 millimeter, and the correction allowance is 4 millimeter, and they are stress at the longitudinous, circumference, and direct, but no stress at bending and torsion. So the stress analysis, the design is considered good because the maximum stress is lower than the allowable stress for the steel, and the elasticity stability is the design ensure good because the compressive stress is the lower than the bulking stress. Okay, the type of vessel support used is the saddle support, and the type flange used is the flange weld flange joint. Okay, this one is the mechanical drawing for the cooler. The one is the top, the up one is the top side, and the bottom one is the side view, and this the round one is the saddle support. This is this, and that one is the saddle at the flange, and the second one is the cross-sectional view.
As a conclusion, the environment is ensured clean since we use EFB as our component in production of glucose under hydrolysis process. The glucose will process under hydrogenation process for production of sorbitol. The plant capacity for our production is 6030 tons per year. Waste management of this plant includes a solid waste treatment and water treatment. For economic analysis, the estimated capital investment and total product cost is RM130 million and 31 million respectively. The estimated payback period is 1.62 years, and net present value shows a positive value. Meanwhile, the discount cash flow rate of return DCFRR is 0.47. Plant location was selected based on a deep geological research which is in Kawasan Perindustrian Kelapa Sawit, Kulai Johor. All of the factors of a good location for a plant is considered before finalizing our plant location. Detailed design and mechanical design have been done for all of the unit and are compared with industrial process so that it will be more realistic and productive.